Hello there. In this video we're going to begin our discussion on improper integrals. And there are several different types of improper integrals. In this video we will only focus on one. So we'll call this our type 1 indefinite integral. So suppose the bounds of an integral, so either one or both, are infinite. And assume that f is finite everywhere on the interval. So what am I talking about? So I'm considering the integrals minus infinity to a of f of x, or the integral a to positive infinity of f of x, or the integral from minus infinity to infinity of f of x dx. And let's assume that here f of x is less than positive infinity and greater than negative infinity on each interval. So what is the interval for the first one? So the first integral is minus infinity to a, the second interval is a to infinity, and this integral would be minus infinity to infinity. And let's assume without loss of generality that these terms are brackets. So we don't have any infinite discontinuities to discuss. We'll discuss them later. So how do we sort of evaluate integrals whose bounds are infinite? So this is a definition. So the integral from a to infinity of f of x is defined to be equal to the limit as m goes to infinity of the integral of a to m of f of x dx. So that's one definition. Two, the integral from minus infinity to a of f of x dx is defined to be equal to the limit as m goes to infinity of minus m to a of f of x dx. And thirdly, the integral from minus infinity to infinity of f of x dx is defined to be equal to the limit as m goes to infinity of the integral from minus m to m of f of x dx. These are the definitions for these three improper integrals. And here we're assuming that a is a finite number, and we're assuming that f is finite on each of these three intervals. If you modify these definitions, you may get different results, but we'll discuss these different results in another video. So let us take these three definitions and just work through a couple examples to sort of see how to work through them. So as our first example, consider the integral from 1 to infinity of 1 divided by x squared dx. By the definition of this improper integral, this is equal to the limit as m goes to infinity of the integral from 1 to m of 1 over x squared dx. Remember that 1 over x squared is a continuous function on the interval 1 to infinity, so that this definition still applies to this function. As long as this interval doesn't overpass 0 or include it, then we won't have any issues. But if it does include 0, either at the endpoint or to the left of it, then you cannot apply this method. So let us consider what this integral is. So we already know that this can be rewritten as the limit as m goes to infinity of the integral from 1 to m of x to the minus 2 dx. So since m is a positive number and not equal to 0, we can apply the fundamental theorem of calculus to this expression. So this is going to be equal to the limit as m goes to infinity of x, so add 1 to that power, so that's going to be minus 1. And then we're going to divide by that new exponent, which is going to be negative. And we need to evaluate this antiderivative of x to the minus 2, evaluated it at m, evaluated it at 1, and subtract. So this is going to be equal to the limit as m goes to infinity of, so the upper limit evaluated, so it's going to be negative 1 divided by m, minus the lower limit evaluated of the function, so it's going to be minus 1 over 1. So what is this equal to? So it's going to be equal to the limit as m goes to infinity of, so we have minus 1 over m plus 1. And now we can apply our limits. So minus 1 over m we know goes to 0. So this is 0 plus 1, which is equal to 1. So therefore, the integral from 1 to infinity of 1 divided by x squared dx is just equal to 1. Let's work through another example. Suppose we have the integral from minus infinity to infinity of 1 divided by 1 plus x squared dx. So since this is an improper integral, we need to refer to the definition of what this actually represents. Remember, this integral is the same as writing, or defined to be equal to, the limit as m goes to infinity of the integral from minus m to m of 1 divided by 1 plus x squared dx. Remember, this function is continuous on the interval minus m to m, because notice the only singularities this function has is at complex numbers. So we can apply the fundamental theorem of calculus to this expression. So remember, FTC only applies if this is continuous on minus m to m, not inclusive of the boundaries. So what is the antiderivative of 1 over 1 plus x squared? So remember that that is the arctangent function. So this is the arctangent function evaluated at x, and we need to evaluate this at m and minus m. So using the fundamental theorem of calculus, let's subtract our limits. So m goes to infinity of, so we have the arctangent of m minus the arctangent of minus m. So remember that arctangent is an odd function, so remember a property of odd functions that f minus x is equal to minus f of x for all values of x in the domain of f. So we can factor this negative out, and that becomes a positive sign. So this is going to be equal to the limit as m goes to infinity of, so we have arctangent plus arctangent, so that's going to be 2 arctangents of m. I can factor out my 2 outside of my limit, so this is going to be equal to 2 times the limit as m goes to infinity of the arctangent of m. So what is this limit? So recall the graph of the arctangent function. The arctangent function has 2 horizontal asymptotes, and it has this type of behavior. So as m, which is the horizontal axis, gets close to infinity, the value of this limit is going to get close to this horizontal asymptote of pi over 2. If it was negative infinity, it would get close to negative pi over 2. So this limit is equal to pi over 2. So that means that this result comes out to pi. So in conclusion, we have that the integral, or the improper integral from minus infinity to infinity of 1 divided by 1 plus x squared dx is just equal to pi. And those are just 2 examples of how to evaluate improper integrals of this form. Now remember, this can only be applied if the function is continuous on the interval of interest and either one of the limits is infinite. If the function is infinite on those intervals, or those values are finite and the function attains infinite values at those boundaries, then you have to approach it in a different way, which we'll discuss in the upcoming videos.